I came out with a model of quantum gravity that is intended for engineering purposes. And I've been working on an experiment. And so I did a write-up here that'll explain what the experiment's about and why I'm doing it. So it's proposed that the gravitational fields may be interpreted as a reduction of the relative available driving power, the watts, of the electromagnetic zero-point field. Gravitational time dilation and length contraction may then be interpreted as a loss of power in the interaction between matter and the zero-point field. It is hypothesized that the loss of power is due to increased radiative damping within matter due to Larmor radiation at the Compton frequency. The relative damping factor affects the relative ground state energy of the quantum mechanical harmonic oscillators such that the mean square fluctuations of matter reproduce the behavior attributed to and resulting from the space-time metric of general relativity. From this principle, the phenomenon observed by a distant observer that are attributed to gravity may be reproduced using a variable relative damping factor acting on the harmonic oscillators of matter. Using nuclear magnetic resonance to stimulate Larmor radiation, experiments may be conducted which demonstrate gravity and anti-gravity accelerations without the need of planetary-sized masses and energies. So just really quick, because this is from my presentation before for those who didn't see it. I use scalar magnetic flux, quantized scalar magnetic flux. This is the basis of resistance because ohms is basically flux per unit charge. And the scalar field is here, and it's the variable that is used to change the gauge in the Lorentz gauge. And this variable has units of magnetic flux. So when you take the derivatives, you get your electromagnetic gauge potentials, but this scalar field has no effect on electric and magnetic fields, for example, because you take the gradient, curl of the gradient, zero. So, but this is the seat of the behaviors that I'm about to discuss. So, assuming, and this is part of the hypothesis, that the Larmor precession frequency is also the Compton frequency at that scale of an electron, just as an example. And that the rest energy of the fermion or electron can be written as mc squared is Planck's constant times the frequency. So, and that frequency would then be the Compton frequency. So we assume that the frequency is the Larmor precession frequency, and then the gyromagnetic ratio times a scalar magnetic flux value gives us this frequency. And that gyromagnetic ratio is given to us as 28 gigahertz per Tesla. And so you back calculate to get the scalar magnetic flux density, which is about 4.5 billion Tesla at the scale of an electron. So that's where your G over C to the fourth comes from. It's a huge number. And that's the energy density in the zero-point field at that scale. But because this is a scalar field that has no direction, and so the statistical average is zero. Okay, so when you have Larmor precession, you have a radiated power, and the fluctuation, the mean square fluctuation in radiated power is this equation. And from the zero-point field, proportional to omega cubed, you get a power fluctuation that is this equation. And when these two are equal, for that particle in that region, space-time is flat. There's no motion in that. There's no curvature or gravitational field. It could be different power values, but as long as these two are equal, then the particle is in equilibrium with the vacuum. And now you introduce a damping factor from the Earth, for example, and it's very small damping factor. But with this damping factor, the power, the square root of this basically, is losing power. The particle is losing power at a rate of 8.76 times 10 to the minus 29 watts per second from its Compton frequency. And that leads to time dilation and length contraction. The proton would be slightly slower, faster. And the good news is that regardless of that 4.5 billion Teslas, a 1 kilogram is losing about 100 watts a second. So that's not an unreasonable number, 100 watts per kilogram per second. So my experiment that I'm working on, and I've been working on this for the better part of 2.5 months now, putting everything together, is to demonstrate I can generate the generation of repeatable nuclear magnetic resonance signals and control of the Larmor precession frequency using a uniform magnetic vector field applied to a sample of deionized water or other material samples. Measure how acceleration due to periodic oscillation of the sample, like bounce the sample on a spring or a rubber band, how that affects, the acceleration affects the change in the Larmor precession frequency. Then apply an oscillating magnetic vector field that replicates the changing Larmor frequency previously measured in an attempt to exert forces on the sample at the same oscillation frequency. So this is grabbing hold of those fermions and trying to exert a force on them all together, all at the same time, all the particles moving, accelerating uniformly. We then apply a static magnetic field vector field gradient and attempt to nullify the weight of the sample. We also do the reverse the field gradient and attempt to increase the weight of the sample, and then repeat for various other materials. Now this is all with a vector field. I haven't yet figured out how to do it with a scalar field. When I do, this list will be repeated. So this is my little lab bench over here, and this is my setup, or the initial part of this setup. I have a pair of Helmholtz coils here, 44 turns. They could generate a field of up to 300 Gauss. And then I have a 9 millihenry coil here that is actually wound in the same direction as the Helmholtz coils, so that I can create a gradient in here. So I can either have a nice uniform field in this area, or I can have a gradient field passing through it. The field lines would be in the same direction, but it would be stronger here, and I can get a gradient this way. So this is a close-up of the coil. Again, it's a, I ordered these in pairs of 2 of them, and they packaged them very poorly, and they knocked together all the way here until the tie wraps broke and the wires came loose, and I had to have them send me another pair, and they did the exact same thing again. So then I had them send me another pair, and I told them to individually wrap them, please, and I finally got a pair that were usable. I found out that in my neighborhood, I have a lot of stray magnetic fields. It varies quite a bit. So I got some at Paul Murad's suggestion. I got myself some high mu 80 sheet metal and built myself a 0 mu chamber, a 0 Gauss chamber. So this is actually 3 layers of high mu 80 mu metal and a bottom. It's 12 inches in diameter, and then another layer that's about a 1/4 inch less than that. And then the inner layer is 8 inches. And so there's a bottom, and these are the results. Where I had 51.3 microtesla previously, now I have 1.7. So it worked quite well. I have a little bit of extra field. Most of it is in the Z component, probably because there's no top on it. But what I did was I added a thin coil here in between to null out that last little bit of Z field. why it keeps doing that. And then this is my pre-polarizing coil, and this is my sample tube. So the sample goes down this tube, which can be weighed or balanced or whatever I want, and it sits inside this coil, and then I can adjust the magnetic field however I need it and take readings. And this coil is then attached to a circuit board that I designed. Excuse me. The schematic is basically a timer with a fourth order bandpass filter, and that coil feeds into a capacitor, making it like an AM radio tuned circuit. So I tune it for the frequency I'm looking for from the resonance of the protons. And then I amplify that with a very sharp filter. And then that signal gets fed out this little SMA connector because my scope probes are way too noisy. And then that goes into my oscilloscope. And then that coil hooks over here to the board, and the MOSFET is used to charge the coil to polarize the water. Then when the coil lets go, it is clamped, the voltage is clamped by this metal oxide varistor and drained very quickly by these resistors. So it's over damped. So I don't have any oscillation. I don't let the voltage reverse or the current reverse, because all I want to do is align the protons along the coil and then let them relax back to the Helmholtz coil field. And in that way, as I can, the harder I polarize them in that direction, the faster I can get them spinning. And then as they relax back down, we'll watch that with the scope and can measure the relaxation time and the frequency. And then varying the magnetic field, I can control the frequency. That's the goal. This is where I'm at right now. So I designed this board, the boards came, I built one using 555 timers, and it would work for one frequency, but I want to try multiple materials and multiple frequencies. So I restuffed the board, and I put 4 capacitors in little sockets so I can change them out and change the value and tune it to different frequencies. And and then I did a Arduino, which now controls it, and I can control the timing and change it to however I want. So I can have a program that works at 2.5 kilohertz for water, and I can have a program that works at 1 megahertz for other materials. And so I should be able to do NMR and electron parametric resonance with this setup, because I can vary both the frequencies, the tuning, and the magnetic fields. And so I made a little magnetic probe here with some Hall effect sensors, which I can drop down in there to test the field and see what strength it is. And with the Arduino, I can actually log that data. But I need the oscilloscope to actually see the signal, because the Arduino is way too slow. And so that's it. That's where I'm at right now. My goal is to, keep working at this. I need to get an accelerometer, and I need to get all this put together and tested and start recording some signals. Seriously, I just finished writing the program today, and it took a couple of days, and stuffing the board took a couple of days, and I had to work too. So it's coming along pretty good, and hopefully soon we'll have some data to share.